Are there questions from anything in the homework? Is anyone looking to see if they're having any questions from the homework? Yes, Alvin. The rest of you who are not Alvin, you need to be quiet so I can hear Alvin. He is far away. Yeah. Oh, graphs pressure. Okay, so let's take a look at that. Honestly, I don't think you're going to end up with pressure in the graphs, but I stole the worksheet from somewhere, so I'm like, okay, let's just go with it. Because sometimes AP will throw you things that you're unfamiliar with, so we might as well get used to dealing with that. So pressure works very much just like concentration, because the more moles of gas you have, the higher the pressure is, okay? So I assume we're looking at something like number 6, yes? Okay, so we would say we have a second order reaction. Therefore, which of these 3 are we using? The last one. So we have 1 over the pressure of NO2, which means partial pressure of NO2, okay? And the partial pressure of NO2 is analogous to concentration of NO2. The higher the concentration is, the larger the mole fraction of NO2, the larger the partial pressure of NO2. Does that make some kind of sense? So at that point, you just say, okay, I'm going to graph it that way. And then on the bottom axis, I'm going to have time, and that's going to be in minutes. And so it is a second order. So which way do we have a positive or a negative slope? Positive. It's second order is the only one with a positive slope. Okay? And that's it. That's all you need to do. Yes. Oh. So we are trying to do, oh, the unit of K. So the unit of K should be y over x. Perhaps I've got the answer key wrong. This is always possible. Y should be 1 over atmospheres, because we've got 1 over pressure over minutes. So unit of K, y over x, 1 over atmosphere over minutes. So it would be atmosphere, -1, minutes, -1. Did I have it wrong in the answer key? Yeah, okay, that would be y. Sorry about that. Fix key. Other questions? Yes? We have a quiz tomorrow. And what is your quiz on? Yes? Potential energy diagrams, kinetic energy diagrams, and reaction mechanisms. Now, actually, coming to think of it, I don't know if you guys have done much in the way of solving reaction mechanisms, so let's make sure that you have. Have you guys done page 96, 97? Have you done 96, 97? Would you like a little time to do it right now? Okay, go. And if you finish 97, you can just keep going 98 to 104. So basically, yeah, just, finish from page 96 to the end. Are you guys focused? Okay, good.
Hello.
Hi. What do we got? Oh, thank you so much. Hi. You might be getting this back today, yes.
Ooh, okay.
Ooh.
So, I don't know what's going on.
Okay, so you have step 1 and step 3, and you have an overall reaction.
Oh, wait a second. Never mind. It's not as complicated as I thought it was.
Okay.
I got confused by all the ion things.
It's okay. It's okay. Okay, where did I put that? Oh, put it right there. So we have Lena, Kim, Lena. Yes. It's like a self-catalyzing reaction. Hi.
So, I've got two reactions here.
Yes.
I've got the one that's catalyzed with NO,
Mm-hmm.
and that's catalyzed with Cl.
Mm-hmm.
Over here, it says, given the uncatalyzed overall slow exothermic, possible graph for the catalyzed. Which one are you asking?
This is question 2. 2. This one. It's not question 1.
I didn't see that there were more than one question.
There you go.
I should pay more attention when I'm doing this. Thank you.
I'm glad your question was so easy to answer.
Yo, I like how like 3 out of the 4 videos they posted on the athletics website was you. Here we go. Yes, I do. Because you told me. This sheet came up to you and told me.
Okay, if I give you guys another like 5 minutes or so to work on stuff, is that okay? And then we'll start some new stuff? Is that okay? Okay, cool. Good.
Oh, yeah, you're right. And sure, did I hear my goat? Yo, explain a small amount. What is it? What's CLFC?
When you hear your name, you can come get your quiz. Jeremy. Oh, by the way, I had my son mark the quizzes. I was sitting right beside him. He's in like 3rd year university or something. So anytime he had a question, he would ask me. I'm sorry his writing looks like a 7-year-old. I don't know what's wrong with him, but anyway, it's all good. So he asked me lots of questions. If you see purple writing, that's him. If you see blue or pink writing, that's me. Okay? Adriana, so if you're like, I don't trust this kid, he's only like whatever, then feel free to ask me if you don't like it. Yoav. Alvin. Elliot. Nathan.
Thank you.
Rigel. Yes. There you go. Evan. Janet. Elvin. Elvin. Ethan. Aaron. Matthew. Godwin. Stephanie. Renard. Amy. Sungha. You get to take it, yeah. Dayun. Sherry. Jude. Isabel. Ruth. Daniel. Armand. Aaron. Idamar. Chloe. Yes.
For like the reactions that we're doing for like steps, right?
Yep.
They get canceled out. It has to be one or the other of reaction intermediate.
That's right.
Balance, right?
Yeah.
Okay.
Hi. So minus 0.25 here, minus 0.25 here, minus 0.5 there. So you need to show that you're finding a change, not just in any old quantity of this, you need to show that it's a concentration. This should have 3 sig figs because it's a subtraction, so your uncertain digit is in the thousandths place, so that makes this 3 sig figs, even though this number only has 2, because subtraction's weird like that, right? And then sig fig. Yeah. Oh, hang on. Oh yeah, units and work, that's the other one, yeah. Yes. Hi.
In my defense, I was
Yes.
going to write nature of reactants, but you said it was one word. So I made
No,
it.
I said it was one of the factors.
Oh.
But you know what? I'll give it to you anyway because you know what? You misunderstood, and that's okay. Maybe I even said it wrong.
I promise you, I was going to put down nature.
Honestly, I believe you, Itamar. You're not like a scammer. I know. Okay. you tomorrow. It's just like people writing paragraphs
Yeah.
about electronegativity and like
Oh yeah, no.
electron
Yeah.
shells, and I'm like, no,
As
just
soon as you
stop
said it was
writing
1
now.
up to 6, I
Yeah.
was like, if nature reacted to it, I heard you say one word.
Oh yeah, no.
It was like the further down you went, like that hotter, like the more flames. So I was like, that might be coming.
There you go.
Thank you so much.
Hello.
I have a question about this. So you know that says like the particles are moving more slowly and
Uh-huh.
less frequency?
Uh-huh.
Like I wrote and less reactions occurred. Did I need to like specify that there were less frequent collision theory?
You need to specifically mention collisions, yeah. Hello.
I was wondering if I get 0.5 instead of 0.25 because it's technically half of this, right?
No.
Okay.
Someone else has the same thing, they also got 0.25. It's okay, don't worry. Honestly, 0.25 on
Let's go!
Okay, friends. We are on 1.6D, which is on page 26. Okay, so we can do a bunch of calculations using the integrated rate laws. We're on page 26. Okay. And just so you remember, we have like a lovely little summary chart here. Okay, so this integrated rate law, we have the y equals mx plus b format. Which we get by using our graph. Yep. And then there is the AP data sheet. Format, which is a typical format to see it in. Okay, it's not just AP data sheet that uses it that way. It's a very typical format to find it in. And then of course we have the unintegrated rate law, which is known as the differential rate law. Not that you need to know that. That's the differential rate law. Yeah, and that's it. Okay, so those are our summaries. Let's take a look at what we can do with this. We can calculate how long does it take, because what we're going to do is we are going to give you 3 of these things. We'll give you K, or a way of finding K. We'll give you A naught, we'll give you A at time t, and then you'll have to calculate T. Yes? We could also give you T and A at time t and ask you to find A naught. Yes. We could give you A naught and ask you to find A at time t. And we could do that for either a 0th order or a 1st order or a 2nd order. So we have to give you everything else and you have to be able to find the missing variable. So not that any of it's particularly hard, but I've given you examples for each of them. So here we have on our next page an example. The rate constant. So we are given the rate constant. This right here is K. How long will it take for 80% of C4H8 to decompose? And the only thing that's tricky about this question is if 80% decomposes, you start with 100%. Right? And then we have 80% decomposes. So what is the concentration of A at time t? If concentration of A naught is 100% and 80% decomposes, what is the concentration at time t? 20%, okay? So basically all you do is you go home, you go around and you collect all your information. So you say the concentration at time 0. There's various ways of writing this. You can say, because it says a percentage, you can just say, I think you can just say 1 if you want to. Yes? Anything? Yeah. We can make up values for 100% concentration and 20% concentration. So we say we have 1.00. Yes? Because that's like 100%. And at time t, we have 20%, so that would be 0.200. And I'm just going to give them all sorts of sig figs and not worry about the sig figs too much here, okay? Now, I'm going to cheat and look at the answer key because I don't actually know what the or was there. Or what? I don't know. $1.60. Oh, here we go. Molar, molar, or you could even do 100 molar and 20 molar. You could do anything you want to as long as it is a 100%, 20% ratio. These are nice round numbers, so either of those will do nicely. We have a value for K, 9.2 times 10 to the minus 3, 9.2 times 10 to the minus 3, and the unit is given as seconds to the negative 1. Now, it tells you in the question what the order is, but I'd like you to look at that K value and tell me if you can tell from the unit what the order is. Yes, first order. Because remember, taking the natural log makes the molarity go, poof, disappear. So molarity is gone. However, most often you'll be told what the order is and not expected to figure it out just from the unit, but we'll practice doing that anyway. And the time, are we given a time? Oh no, time is what we want to figure out. We don't know how many seconds. Good, okay, we need to have an unknown. So we choose which formula to plug it into. Which one do we want? Okay, take a look at it. We have option A, option B, option C. Option A, option B, option C. Which would you like to choose? B. Okay, because this is zeroth, this is first order. This is second order. Okay. Then we solve the equation for T, plug in the concentrations, and do the math. Could you do that algebra for me, please? Just practice your algebra. Did you take into account that K is negative? That's why we practice these, because, you know, just the algebra and dropping negative signs, that was always my favorite trick. Okay, so I'd like you to check. If you finished, I'd like you to check your work. See that you wrote the formula. See that in your work you showed the units. And remember, what does ln do to units? Disappear. Okay. And so we're left with seconds to the -1 in the basement, which gives us seconds to the +1, which is just seconds. And 2 sig figs, and that's it. Is good? Excellent. Shall we do the next one? All right. How much remains after a given time? The reaction of butadiene produces C8H12 gas as follows. The reaction is second order, so we can fill that in, second order. The rate constant is 5.76 times 10 to the -2 liter per mole per minute. So just go data mining in your question. Just be like, what numbers do I have in my question? If the initial concentration of butadiene is 0.200 molar, what is the concentration remaining after time 10.0 minutes? Which version will we plug everything into? Far right, because we're second order, yes? And you could recognize from the unit that we have molarity upside down, right? 1 over molarity, right? And we have 1 over molarity here. And that gives us our second order. Solve the equation for, it should not say for T, it should say solve the equation for concentration of A to the T. However, what you'll notice is it's way easier to solve for 1 over and then just flip it at the very end. Okay, so I wouldn't bother doing the inverse until the end. So do the algebra on that, see how that goes. I see puzzled brows. Where? What did you do? Where did you go wrong? You know where you went? Okay. Yes. What's that? I think so. Let me see. Yeah, it's 1 page, front and back. There's diagrams, things for you to draw, things for you to define, reaction mechanisms for you to solve. Yeah. How are we doing? Are we good? Okay. Should we do the next one? Or are we getting the idea and we're like, we don't need to do anymore? What do you guys think? Okay, either we're getting the idea and we don't want to do anymore because we're just going to be solving for other like missing pieces, right, given whatever we have. Or you can be like, no, let's do one more. So yes, let's move on. No, let's do one more. Yes, let's move on. No, let's do one more, sort of in the middle. Okay, so we're going to move on, but if you would like to do another example with me at some point, we may have time to do that later. When is class over today? 44. Okay, so we can go back and do it more later if we need to. So for this, maybe when you go home, you could do numbers 1 and 2, just for argument's sake. Okay, so homework, do number 1 and 2. Let's talk about half-life then, which is on page 32. How many of you have heard of half-life before? Maybe in physics, maybe in science 10, something like that. It's usually a decay process where something breaks down, and half-life is the time it takes for the initial reactant concentration to decrease to 1/2 of what it originally was. Okay? Now, half-life varies depending on whether you have a zero-order reaction, whether you have a first-order reaction, or whether you have a second-order reaction. So if we look at this particular 0th order, of course, the concentration of A versus time is a straight line. So it takes that much time there to get cut to half the original concentration. But what do you notice about the time it gets? So that's going from 100% to 50%. What do you notice about going from 50 to 25? What happens to the half-life? It gets halved. And then the third half-life to get to 12.5, again, it gets halved, so it's a quarter, okay? So you do not have a consistent half-life if the reaction is 0th order. First order, if we graph concentration of A versus time, we're not doing any integrated graphing, we're just graphing concentration of A versus time, and we get a curve so that we can see that our first half-life is the same length as the second half-life is the same length as the third half-life, okay? So here for first order, we have a consistent half-life. And quite frankly, I think this is all AP cares about, is first order half-life, okay? So you can be like, yes, it's nice that 0th order doesn't have a constant half-life. It's nice that half-life decreases over time, but they're probably not gonna ask me about that, okay? And same thing for second order. You can see the curve is it's more curvy curve. And so in fact, the half-life gets greater over time. So we have a shorter first half-life, longer second half-life, and an even longer third half-life. So not a constant half-life. So you can tell that a reaction is 0th order if the half-life does what with decreasing concentration? Decreases. You can tell that you have a first order if concentration of A gives a half, shows that half-life stays the same. with decreasing concentration, and you can tell you have second order if A versus T shows that the half-life increases with decreasing concentration. Okie dokie. Like I said, you probably don't care about the 0th and the 2nd. And I even wrote that here, to be honest. I don't know if AP cares if you know the relation between the half-life and the decreasing concentration for the various orders. I believe they only care about first order half-lives, and there are 3 things that you need to know about first order half-lives. And the first one you already know, you know that the half-life is constant. Second thing you need to know is if you are dealing with radioactive decay is always just first order, okay? And you need to know that the formula relating half-life and the rate constant K is given in the AP data pages, and this is for first order reactions, okay? So most everything you can do just by halving and halving and halving concentrations and using this formula, okay? So there's not a lot to it. It's not like a huge component of the curriculum. Yes? I don't know. All I know is this. Yeah, because there's like, yeah, there's an E in here somewhere. Yeah, because there's a natural log in there somewhere. Math, me. Okay, so here's just a little illustrative picture. If you haven't had a lot of exposure to half-life, you can see that if I have cobalt 60, I start with 10 grams, and then I have 5 grams, and then I have 2.5 grams, and I just keep halving the mass of the cobalt 60, which is decomposing into other things over time. Radioactive decay follows first order reaction kinetics. We already said that. Okay. One simple way of solving some half-life problems is just to write out the times and amounts for each half-life. So our first example here, sodium-24 has a half-life of 15 hours. If we start with 64 grams of sodium-24, let's fill in this chart for how much we have after each time interval. How much do we have after 15 hours? Remember, our half-life is 15 hours. 32 grams. At 30 hours, how much do we have? 16 grams. And then we can go and fill in all the rest. We can say, okay, I got 30 hours. What's next? 45, 60, 75, 90, 105. And then you just need to be able to do your powers of 2. Yeah, so we go from 64 to 32 to 16 to, yes, to 8 to 4 to 2 to 1 to 0.5. Okay, so you can often just do things like that. So if they're like, you know that it has a half-life of 15 hours, how much is left after 60 hours? You can be like, well, 60 hours is 1, 2, 3, 4 half-lives to get to 60 hours. And so at 60 hours, we'll have 4 grams left. Okay, so you can do things like that. Using the half-life formula and the integrated rate law, and remember this is for first order, and this is our first order integrated rate law. You can derive the half-life formula, this one here, by doing some algebra on this integrated rate law, which is what you were talking about with like the E and everything, but we ain't got no time for that. Okay, so if you are interested in doing that, you can do that on your own. We're just going to go ahead and use the formula as given. The half-life of a first order reaction is 35 seconds. Calculate the rate constant. Those are the answers, okay? And calculate the time for 95, this is the answer, okay? So you can check your answer. So start by solving for K because you want to find the rate constant. Yes? It's on the data sheet, yes, yes. So if you look on your data sheet, we have 0th order, integrated rate law, first integrated rate law, second integrated rate law, and the half-life for first order. Yes? Oh, why am I doing that? It should be right here. Did I not put an answer key to number 2? That's okay. We can do this. Did you guys get that for K? Did you do it or did you just let me do it? Okay, good, 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 good. Now for the second one, we need to calculate the time required for 95% to decay. So what formula would we be wanting to use here? If we want to find the time required for 95% of the sample to decay, we would be wanting to use the integrated rate law for first order because we can solve that. So we're going to be using integrated rate law for first order. Now, after 95% is decayed, how much is left? 5. So if we let A naught equal 1 molar, you can choose any values, but starting with 1 molar tends to make your math simple, especially because the ln of 1 is 0. Isn't that nice? So if you let your initial molarity equal 1, when you take the natural log of 1, you get 0, which just makes life super nice. Yes? So you solve the integrated rate law for T. Okay, so we have all of this. We plug in all our numbers. Did I forget a negative here? This should be T. Oh no, I got my negative here. I put my negative there. Okay, you could put the negative there and not have it there. That would also be fine. Okay, there we go. Use the unrounded value. Don't round off until you absolutely have to. And be sure to make this let statement. Yes? What is the half-life of this element if the rate constant is that many days? And if they ask you for the half-life, these are super simple. You're like, oh my gosh, I got a half-life and I got a K and I got a formula that relates half-life and K. You know, so I mean, you can see the math is there, but it's really straightforward. Yes? Of course. Okay, this one's a little more complicated. Copper 64 has a half-life of 12.70 hours, what percent of copper 64 remains? So that's going to be concentration of Cu at time t. In order to solve for a concentration at time t, what else do you need that the question has not yet given you? You need the rate constant. So you're going to find the rate constant using this equation, yes? And then once you have found the rate constant, don't forget your let statement. Remember. Okay, so now we're taking our rate law from the data booklet and we're rearranging it to solve for ln of A at time t. Calculation, 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 throw in the numbers, and you have now solved for ln of A at time t. Do you know how to get to concentration of A at time t from the ln of A at time t? If you haven't done natural logs, what you need to do is you need to do the opposite of natural logging it. And the opposite of natural log is e to the whatever. So basically what we're doing here is we're taking e to the ln A at time t is equal to e to the negative 0.3492. Yes? So when we take e to the ln AT, we get A at time t. And when we get e to the negative 0.3492, we get that. And we just throw that in the calculator. Okay? And on your calculator, usually above the ln button, there is second function e to the x. So see if you can find that on your calculator and do this calculation here. Make sure you're good with that calculation there. Yes? This is entirely possible. Where is the error? Oh, you are right. It should be negative 3.492, which would give us different answers. And yes. Yes. Okay. So let's see what it should be. This should be negative 3.492. Does it? Oh, so maybe I had, you know what I probably did? I probably had the answer in my calculator, and then I used that number, but I typed it wrong. So that's my guess. Oh, 0.034, yeah. Okay, so this is correct. This part here is correct. And we are out of time. Your homework is just to study for your quiz. Okay, so all of anything you've not done in 1.3, 1.4, 1.5 is up for grabs. Nothing from the AP is on the quiz, just study or on the test. Except for the AP test. Yes?
This one, we can set like
Any value you want. One is usually convenient because it makes your calculations easy. Yep. Howdy. Nope, you get to keep it.
Oh, cool.
Study from it, whatever you like. Yes.
Or with this one.
Mm.
Are we supposed to mention, like, if this comes up on the AP exam, both that the average energy decreases and that the number of collisions decreases?
Yes.
Okay, great.
Hi. You mean like